Long before the first Tyrannosaurus rex ever left a footprint, our planet was transformed into a realm of astonishing complexity and scale, a world that would lay the groundwork for much of the life that followed. Imagine, if you will, a time when the very air was saturated with oxygen, levels reaching up to 35%, nearly double what we breathe today, making the atmosphere denser, more reactive, and fundamentally altering the physiology of life. This was the Carboniferous Period, a pivotal era in Earth's history that spanned from approximately 359 to 299 million years ago, bridging the gap between the Devonian and Permian periods. It was an age not of dinosaurs but of immense arthropods and lush, sprawling forests, ecosystems dominated by organisms that would seem otherworldly to us today. The planet's climate was equatorial and monsoonal, with vast lowland swamps and wetlands stretching across supercontinents, shrouded in a perpetual, moisture-laden haze. The evidence of this world is preserved in the thick seams of coal that power our modern civilization, remnants of ancient forests, compressed and fossilized over millions of years, holding within them the story of a vanished biosphere. To truly grasp the Carboniferous, we must set aside our familiar images of prehistory and envision a planet utterly transformed by its own evolutionary experiments. There were no flowers to color the undergrowth, no birds to fill the air with song, and no mammals to scurry beneath the ferns, only the relentless proliferation of spore-bearing plants and the earliest seeds. This was a primordial kingdom ruled by amphibians, some as large as crocodiles, and, most spectacularly, by arthropods, the lineage that includes insects, spiders, and millipedes, many of which reach sizes unimaginable today. These creatures were the undisputed giants of their time, thriving in an environment that pushed the boundaries of biological possibility. The unique atmospheric conditions, high oxygen, stable temperatures, and abundant plant matter did not merely permit their growth, they drove it, enabling evolutionary experiments in gigantism rarely seen before or since. The Carboniferous is a breathtaking chapter in the story of life, marked by rapid evolutionary innovation and the emergence of complex terrestrial ecosystems, all shaped by the interplay of climate, geology, and biology. Our journey takes us back across a vast ocean of time, to a world where continents drifted and collided, shaping the geography and climate in ways that would define the future of life on Earth. The landmasses we now know as North America and Europe were converging with the immense southern continent of Gondwana, triggering mountain-building events and altering global weather patterns. This monumental geologic choreography was forging the supercontinent Pangaea, setting the stage for dramatic shifts in ocean currents, climate, and the distribution of life. Along the equator, where these continents met, a vast belt of warm, stable, and humid climate emerged, fostering the growth of immense coal-forming forests and supporting unparalleled biodiversity. This tropical zone became the cradle for an explosion of life, a greenhouse world where dense canopies of lycopsids, horsetails, and ferns created habitats for a dazzling array of amphibians, arthropods, and the earliest reptiles. So, let us step into this lost world, a realm where every breath was thick with moisture and the scent of decaying vegetation, and where the cycle of life and death built the very foundations of our modern landscapes. Here, the air vibrates with the beating wings of dragonflies the size of hawks, and the forest floor trembles beneath the passage of millipedes longer than a grown human. It is a story of how a unique atmospheric chemistry, driven by the relentless photosynthesis of vast plant communities, created a temporary paradise for giants while simultaneously locking away carbon and shaping the planet's future climate. The Carboniferous reminds us that the rules of life are not fixed, they are sculpted by the ever-changing interplay of atmosphere, geology, and biology, a dynamic system that continues to evolve to this day. The Carboniferous stands as a testament to nature's boundless creativity and its capacity for producing wonders that challenge our imagination, offering a glimpse into a world both alien and foundational to the story of life on Earth. The Carboniferous Period, spanning from roughly 359 to 299 million years ago, was a time of profound atmospheric transformation. The most defining feature of this era was the unprecedented rise in atmospheric oxygen, a phenomenon that would forever alter the trajectory of life on Earth. Modern atmospheric oxygen levels hover around 21%, but during the Carboniferous, this concentration surged to approximately 35%, the highest in Earth's history. This dramatic increase was not a mere fluctuation, but a fundamental shift in the planet's environmental and biological systems. The source of this oxygen revolution was the vast, unbroken forests that blanketed the continents. These forests were dominated by primitive vascular plants, towering lycophytes, giant horsetails, and immense tree ferns, species that thrived in the warm, humid, and swampy lowlands of the Carboniferous world. Through the process of photosynthesis, these plants absorbed immense quantities of carbon dioxide, using sunlight to convert it into organic matter. The byproduct of this process was oxygen, which was released in staggering volumes into the atmosphere. The scale of this photosynthetic activity was unprecedented. Dense, swampy forests stretched across equatorial regions, forming what scientists call coal forests. These ecosystems were so productive that they acted as planetary-scale oxygen generators, fundamentally altering the composition of the air. The environmental impact of this oxygen surge was profound. Elevated oxygen levels increased atmospheric density, which in turn influenced global climate patterns, fire regimes, and even the physiology of terrestrial organisms. For example, the high oxygen content enabled arthropods and amphibians to attain enormous sizes, as their respiratory systems could efficiently extract oxygen from the air. But the true key to this atmospheric transformation lay in the fate of the plant material after death. Unlike today, where fallen trees and plants are rapidly decomposed by fungi and bacteria, the Carboniferous swamps were low in decomposer organisms. The waterlogged, anoxic conditions of these swamps inhibited decay, causing dead plant matter to accumulate in thick, organic, rich layers. Over millions of years, these layers were buried by sediment, locking away vast amounts of carbon underground. This process, known as carbon sequestration, prevented the return of carbon dioxide to the atmosphere and allowed oxygen levels to continue rising. The burial of organic matter not only fueled the oxygen boom, but also laid the foundation for the world's extensive coal deposits. Under immense pressure and heat, these ancient plant remains were transformed into coal seams, hence the name Carboniferous, meaning coal-bearing. The consequences of this oxygen-rich world were far-reaching. Wildfires became more frequent and intense as high oxygen concentrations made vegetation more flammable. The chemistry of soils and oceans shifted, influencing nutrient cycles and the evolution of new life forms. Ultimately, the rise of oxygen during the Carboniferous era was a pivotal event in Earth's history. It set the stage for the evolution of complex terrestrial ecosystems and paved the way for the emergence of large, active animals in the eras that followed. The legacy of this ancient oxygen revolution is still visible today, both in the coal seams beneath our feet and in the very air we breathe. To wander through a Carboniferous forest would be to step into a world utterly unlike any modern ecosystem, a realm dominated by botanical giants and evolutionary marvels. The air, saturated with moisture and oxygen, pressed down beneath a dense, interlocking canopy. Sunlight filtered through layers of foliage, casting the forest floor into a dim, perpetual twilight, where only the hardiest shade-loving plants could thrive. The dominant vegetation was unlike anything alive today. Instead of familiar flowering trees, the landscape was ruled by primitive vascular plants, towering lycophytes, colossal horsetails, and immense ferns, each representing a unique evolutionary experiment in size and structure. Among the most spectacular were the lycophyte trees such as Lepidodendron and Sigillaria. These so-called scale trees could reach heights of over 30 meters, their trunks rising straight and unbranched for much of their length before exploding into a crown of slender, spiraling leaves. Lepidodendron, though often mistaken for a true tree, was actually a giant club moss. Its vascular system was primitive, with most of its support coming from a thick outer bark-like layer, while the inner tissues remained soft and spongy. The trunk was marked by a distinctive diamond-shaped pattern, leaf scars left behind as old leaves dropped away. This gave Lepidodendron a reptilian, almost alien appearance, and provided clues to its rapid growth and unique method of photosynthesis. Beneath these towering lycophytes, the understory was a dense tangle of vegetation. Here, ancient relatives of modern ferns and mosses formed a living carpet, their fronds and leaves competing for every scrap of filtered light. Tree ferns, some with fronds stretching over 6 meters, unfurled in the humid gloom. Their arching leaves created a secondary canopy, intercepting moisture and providing habitat for countless invertebrates. Interspersed among the lycophytes and ferns were the calamites, giant relatives of today's horsetails. These plants, with their segmented hollow stems, could grow up to 20 meters tall and formed dense bamboo-like thickets along the swampy margins. Unlike their modern descendants, which rarely exceed a meter in height, Carboniferous horsetails developed woody tissues for support. Their jointed stems and whorled branches maximized photosynthetic area and allowed them to thrive in waterlogged soils. The forest floor was a living, breathing mat of mosses, liverworts, and decaying plant debris. Instead of rich soil, a thick layer of peat and organic matter accumulated, slowly compressing over millions of years to form the coal beds we mine today. Visually, the Carboniferous forest was striking for its monotony. There were no flowers, no fruits, and no bright colors, just endless shades of green and brown, broken only by the occasional spore-producing structure. Flowering plants or angiosperms would not appear for another 150 million years. The entire ecosystem was built upon the success of spore-bearing plants, which relied on water for reproduction. Without flowers or fruits, the forest lacked the vibrant hues and scents that attract pollinators today. Instead, reproduction depended on the dispersal of microscopic spores carried by wind or water across the swampy expanse. The result was a world painted in subdued tones, where the interplay of light and shadow created a mysterious, almost otherworldly atmosphere. The soundscape was equally alien. There were no birds to sing, no bees to buzz, only the whisper of wind through fronds and the distant splash of amphibians. Insects, some of them enormous by modern standards, filled the air with a constant hum and clatter. The high oxygen levels allowed dragonflies with wingspans over 70 centimeters and millipedes as long as 2 meters to thrive among the foliage. The flora of the Carboniferous was exquisitely adapted to its wet, low-lying environment. Many plants developed specialized tissues for water transport and storage, while others evolved aerial roots and buttresses to anchor themselves in the unstable, swampy ground. Shallow, spreading root systems were essential for stability, as the saturated substrate could not support deep roots. These adaptations allowed the forests to colonize vast tracts of equatorial wetlands. Reproduction was entirely dependent on water. Spores, rather than seeds, were released in staggering quantities, and fertilization required a film of water, tying the life cycles of these plants to the ever-present swamps and seasonal floods. This reliance on water shaped the distribution of Carboniferous forests, which blanketed the equatorial regions in vast, unbroken swathes of green, forming one of the most extensive wetland ecosystems in Earth's history. These forests were the foundation of the Carboniferous world. Through photosynthesis, they pumped vast amounts of oxygen into the atmosphere, raising levels to nearly double those of today, and laid down the organic material that would become the coal deposits, fueling our modern civilization. Their ecological legacy shaped not only their own era, but the entire course of life on Earth. The Carboniferous Period, spanning from roughly 359 to 299 million years ago, was a time of extraordinary transformation on Earth. Vast, humid lowland forests stretched across ancient continents, dominated by towering lycopsides like Lepidodendron and Sigillaria, immense horsetails and dense mats of ferns. These primeval forests were not only visually striking, but they also played a pivotal role in shaping the planet's atmosphere and fueling the rise of giant life forms. The relentless growth and decay of these plants produced immense quantities of organic material. As dead plant matter accumulated in waterlogged swamps, it formed thick layers of peat, which over millions of years would become the coal deposits we mine today. This process not only locked away vast amounts of carbon, but also released oxygen as a byproduct of photosynthesis. The result was an atmosphere with oxygen levels soaring up to 35%, far higher than today's 21%. This oxygen-rich air was the key that unlocked a new biological potential, gigantism, especially among arthropods. Unlike vertebrates, which rely on lungs and a circulatory system to transport oxygen, insects and other arthropods breathe through a network of tiny tubes called tracheae, which open to the outside world via small holes called spiracles. Oxygen enters these tubes and diffuses passively through the network, reaching deep into the insect's body tissues. This system is highly efficient for small creatures, but it has a fundamental limitation. As an insect grows, its volume increases much faster than its surface area, making it harder for oxygen to reach the innermost tissues. In today's atmosphere, this imposes a strict upper limit on insect size, but in the Carboniferous, the much higher oxygen concentration created a greater pressure gradient, effectively pushing oxygen deeper into the tracheal tubes with far less effort. This supercharged oxygen supply allowed insects and other arthropods to overcome the size limitations imposed by their respiratory systems, evolving to sizes that seem monstrous to us today. But oxygen was not the only resource fueling this age of giants. The geological context of the Carboniferous was equally important. The continents were clustered near the equator, creating vast tropical wetlands with stable, warm and humid climates. These conditions promoted year-round plant growth and high primary productivity. The abundance of plant life provided a continuous supply of food and shelter for herbivorous arthropods, while decaying organic matter supported a thriving community of detritivores and decomposers. The nutrient-rich soils and constant recycling of organic material created a stable foundation for complex food webs, supporting not only giant insects and millipedes, but also early amphibians and diverse plant-eating arthropods. The dense, moisture-laden air of the Carboniferous also played a crucial role. With higher concentrations of oxygen and other gases, the atmosphere was thicker, providing greater aerodynamic lift for flying insects. Paleoaerodynamic studies revealed that this denser air made it easier for large insects to take off, stay airborne, and maneuver through the forest canopy, reducing the energy required for flight by as much as 25%. The very air they moved through supported their enormous bodies, while the lush vegetation below provided ample food and shelter. With abundant oxygen and plentiful resources, arthropods could sustain higher metabolic rates, fueling rapid growth, powerful muscles, and active lifestyles. Dragonflies like Meganeura could grow wingspans of over 70 centimeters, while millipedes such as Arthropleura reached lengths of more than 2 meters, feats made possible by the unique combination of atmospheric, geological, and biological factors. Gigantism was not merely a possibility, it became an evolutionary advantage, allowing these creatures to dominate their environments and exploit new ecological niches. The Carboniferous atmosphere, dense and oxygen-rich, was a world fundamentally different from our own, a world where the resources of land, air, and plant life converged to create the perfect conditions for giants. In this ancient, thriving ecosystem, the giants of the Carboniferous did not merely survive, they flourished, forever shaping the course of life on Earth. The Carboniferous skies were dominated by one of the most formidable aerial predators ever to exist, Meganeura, a true giant among insects. Meganeura was not a dragonfly in the modern sense, but a member of the extinct order Meganeura griffinflies, whose lineage diverged from today's odonates over 300 million years ago. Its wingspan could reach an astonishing 70 centimeters, dwarfing any living insect and rivaling the size of a modern crow. The wings themselves were reinforced with a dense network of veins, providing both strength and flexibility for sustained flight. These two pairs of intricately veined wings allowed Meganeura to maneuver with remarkable agility through the tangled, humid forests, darting between colossal ferns and towering club mosses in pursuit of prey. Its head was dominated by enormous compound eyes, each composed of tens of thousands of ommatidia. This provided Meganeura with a nearly 360-degree field of vision, enabling it to detect the slightest movement of potential prey or rivals in the dense undergrowth below. Meganeura's predatory behavior was highly specialized. It likely ambushed other large insects, such as primitive mayflies and early cockroaches, and may have even preyed upon vulnerable juvenile amphibians near the water's edge, using its powerful mandibles to pierce and consume soft-bodied victims. Its spiny, raptorial legs were held forward in flight, forming a basket-like trap to snatch prey mid-air. Once captured, the prey would be immobilized by the sharp spines and swiftly devoured. The sight of Meganeura gliding effortlessly through the primeval foliage, its wings shimmering in the filtered sunlight, would have been both mesmerizing and intimidating, a testament to the evolutionary arms race of the Carboniferous. The extraordinary size of Meganeura was made possible by the Carboniferous atmosphere, which contained up to 35% oxygen, nearly double today's levels. This abundance of oxygen allowed for more efficient diffusion through the insect's tracheal system, supporting much larger body sizes than are possible in the modern world. In today's oxygen-poor environment, such a giant would be physiologically impossible. The limitations of passive respiration in insects mean that only in the high-oxygen Carboniferous could these megabeasts thrive. While Meganeura ruled the air, the forest floor was dominated by Arthropleura, the largest terrestrial invertebrate ever discovered. This colossal millipede relative was a marvel of evolutionary engineering. Arthropleura could reach lengths of up to 2.5 meters and widths of nearly 0.5 meter. Its segmented, armored exoskeleton provided protection from predators and supported its massive bulk as it navigated the dense leaf litter. The body of Arthropleura was composed of dozens of articulated segments, each bearing a pair of robust, jointed legs. This design allowed it to move with surprising speed and flexibility despite its size. Fossilized trackways, preserved in ancient mudstones, reveal that Arthropleura was an active and mobile forager, capable of traversing vast stretches of the Carboniferous forest floor in search of food. Despite its fearsome appearance, Arthropleura was a strict herbivore. Its mandibles were adapted for slicing through tough, decaying plant material, and its digestive system was specialized for extracting nutrients from the abundant detritus covering the forest floor. In the shadowy undergrowth, another formidable arthropod prowled, Pulmonoscorpius, the breathing scorpion. This ancient predator was a master of ambush and stealth. Pulmonoscorpius could grow up to 1 meter in length, making it one of the largest scorpions ever to walk the earth. Its heavily armored exoskeleton and powerful pincers made it a dominant predator of the Carboniferous forest floor. The name Pulmonoscorpius refers to its advanced book lungs, layered respiratory organs that enabled efficient gas exchange. This adaptation allowed it to exploit the oxygen-rich air and grow to sizes unimaginable for modern scorpions. Its pincers, or chellae, were robust and muscular, capable of exerting a crushing force comparable to the bite of a small crocodile. This allowed Pulmonoscorpius to overpower armored prey, such as early amphibians and other large arthropods. At the tip of its segmented tail, Pulmonoscorpius wielded a venomous stinger, likely delivering a potent neurotoxin to immobilize or kill its prey. This combination of brute strength and chemical weaponry made it one of the apex predators of its time, perfectly adapted to the lush, perilous world of the Carboniferous. The Carboniferous era's supercharged atmosphere, with oxygen concentrations soaring to nearly 35%, fundamentally altered the planet's chemistry and climate. This oxygen-rich air, while fueling the rise of giant arthropods and lush forests, also created a world fraught with peril. The high oxygen content dramatically increased the flammability of the landscape. Even the dampest, greenest vegetation, normally resistant to ignition, became susceptible to fire. In this environment, the energy required to spark combustion was drastically reduced, making wildfires not just possible, but inevitable. Lightning strikes, frequent in the warm, humid climate, could ignite vast swathes of forest with a single bolt. Once started, fires would rage with an intensity and speed far beyond anything seen in the modern world. The flames could leap from treetop to treetop, consuming entire forests in hours and generating immense plumes of smoke that blanketed the land. These wildfires were not isolated events. Geological evidence, such as thick layers of fossilized charcoal known as fusan, found in Carboniferous rock strata across the globe, reveals that continent-spanning infernos were a recurring feature of this era. These layers are the unmistakable signatures of ancient firestorms that reshaped entire ecosystems. The atmospheric science behind these fires is striking. With so much oxygen, the heat released during combustion was far greater, and the resulting fires could reach temperatures high enough to alter soil chemistry and even affect atmospheric circulation. The smoke and ash injected into the air would have dimmed sunlight, cooled local climates, and contributed to a cycle of destruction and renewal. For the creatures of the Carboniferous, survival was a constant challenge. Giant insects, like Meganeura, may have used their powerful wings to escape above the smoke and flames, while ground-dwelling arthropods such as Arthropleura likely sought refuge by burrowing deep into moist soil or retreating to the safety of swampy waters. Amphibians, bound to aquatic habitats, were shielded from the worst of the fires, unless their pools evaporated in the intense heat. The relentless threat of fire exerted powerful selective pressure on all life. Only those species capable of rapid escape, effective burrowing, or aquatic refuge could persist. Over time, these survival strategies shaped the evolution of Carboniferous fauna, favoring mobility, adaptability, and resilience. On a planetary scale, these wildfires played a crucial role in Earth's carbon and oxygen cycles. While they released vast amounts of carbon dioxide, much of the plant material was only partially combusted, forming charcoal that resisted decay. This charcoal, buried in sediments, locked away carbon for millions of years, further amplifying the oxygen-rich conditions. The Carboniferous world was thus a paradox, a lush, vibrant landscape perpetually threatened by its own atmospheric bounty. The very air that enabled life to flourish also set the stage for destruction on a scale rarely matched in Earth's history. For over 60 million years, the Carboniferous period fostered a world teeming with life, its vast swamp forests and oxygen-rich atmosphere supporting some of the largest arthropods and amphibians ever to exist. Yet, as with all chapters in Earth's history, this era of abundance was destined to close. Around 305 million years ago, the planet underwent a profound transformation. Global temperatures began to fluctuate, and rainfall patterns shifted, marking the onset of a dramatic climatic upheaval. The relentless drift of tectonic plates was culminating in a monumental event, the assembly of the supercontinent Pangaea. As the scattered landmasses merged, they formed a single immense continent, fundamentally altering the planet's geography and climate. This reconfiguration disrupted oceanic circulation, reducing the transfer of heat and moisture between the equator and the poles. Ocean currents faltered, and the once stable weather systems became unpredictable, leading to increased seasonality and regional extremes. The heart of Pangaea, isolated from the moderating influence of the oceans, became a vast, arid expanse, subject to extreme temperature swings and prolonged droughts. Lush equatorial forests gave way to seasonal woodlands and open plains as rainfall diminished and the climate grew increasingly erratic. The once continuous tropical belt, which had nurtured the cold-forming swamps, began to fragment, its forests shrinking and breaking apart. Meanwhile, in the southern hemisphere, the supercontinent Gondwana drifted over the South Pole, triggering the growth of massive glacial ice sheets. These glaciers expanded across what would become Antarctica, Australia, and South America. The onset of this ice age locked away vast amounts of water, causing global sea levels to plummet and exposing new stretches of barren land. The great swamp forests, once stretching unbroken for thousands of kilometers, began to wither and die as their habitats dried out. This environmental crisis, known as the Carboniferous rainforest collapse, shattered the vast jungles into isolated fragments, each surrounded by inhospitable terrain. These ecological islands became refuges for surviving species, but many organisms were unable to adapt to the new, harsher conditions. The extinction toll was severe. Giant lycophyte trees and tree ferns, which depended on constant moisture and spore-based reproduction, suffered catastrophic declines. These towering plants, once the architects of the Carboniferous landscape, vanished from most regions, unable to survive the prolonged droughts and seasonal fires. In their place, hardier seed plants such as conifers and early relatives of modern cycads began to dominate, better equipped to withstand arid conditions and reproduce without standing water. The collapse of the swamp forests triggered a cascade of extinctions among the animals that depended on them, including many giant arthropods and amphibians. As plant biomass dwindled, the planet's oxygen production plummeted, and the once thick oxygen-rich air began to thin. Large-scale photosynthesis ground to a halt, and the burial of organic carbon slowed dramatically, reducing the drawdown of atmospheric carbon dioxide. Simultaneously, geological processes such as weathering and volcanic activity continued to consume atmospheric oxygen, further accelerating the decline. Oxygen levels, once peaking at an extraordinary 35%, fell sharply, approaching the lower levels characteristic of the early Permian. The very air that had enabled the reign of Carboniferous giants was fading, ushering in a new era of evolutionary challenges and opportunities for the survivors. The Carboniferous world, once dominated by towering forests and colossal arthropods, began to unravel as atmospheric oxygen levels sharply declined. This drop was not a sudden catastrophe, but a gradual, relentless shift that fundamentally altered the physiology and survival of the era's giants. The immense size of arthropods like Meganeura and Arthropleura was made possible by an atmosphere rich in oxygen, levels reaching up to 35%, nearly double today's concentration. Their respiratory systems, based on passive diffusion through tracheal tubes, could only function efficiently in such an environment. As oxygen content fell, these tubes became bottlenecks, unable to deliver enough oxygen to sustain massive bodies. The once thriving giants found themselves suffocating, their tissues starved for air. The fossil record reveals a dramatic reduction in arthropod size, with the largest forms vanishing first, followed by a steady decline in diversity and abundance. Over millions of years, the lush swamps that had fueled high oxygen production dried up, their collapse triggered by tectonic shifts, climate change, and the evolution of lignin-degrading fungi that broke down plant matter, reducing oxygen output. As the forests withered and the wetlands receded, the intricate web of life that supported the giants unraveled. The extinction of these vast ecosystems led to a cascade of evolutionary consequences. The disappearance of giant arthropods left ecological niches vacant, while smaller, more adaptable insects survived by virtue of their lower oxygen requirements and flexible life strategies. Simultaneously, amphibians, once dominant vertebrates, struggled with the increasingly arid conditions. Their reliance on moist environments for skin respiration and reproduction became a severe limitation as the climate shifted toward greater dryness and seasonality. In this crucible of change, the reptiles emerged as evolutionary innovators. Unlike amphibians, reptiles possessed keratinized, scaly skin that minimized water loss, allowing them to venture far from water sources. The evolution of the amniotic egg, a self-contained aquatic environment, freed them entirely from the need to lay eggs in water, a revolutionary adaptation that opened up vast new territories. Early reptiles, such as Hylonomus and Paleothyrus, began to exploit the drier uplands and forest margins, habitats previously inaccessible to amphibians and giant arthropods. Their ability to regulate water loss, combined with internal fertilization and protective eggs, gave them a decisive advantage in the changing world. As the Carboniferous gave way to the Permian, reptiles diversified rapidly, filling ecological roles left vacant by the extinction of the giants. They became the new pioneers, spreading across the supercontinent of Pangaea, adapting to arid plains, rocky uplands, and shrinking wetlands. This evolutionary transition marked a profound ecological shift, the end of the reign of giant arthropods and amphibians, and the dawn of vertebrate dominance. The rise of reptiles set the stage for the great evolutionary dramas of the Permian and Mesozoic, ultimately leading to the emergence of the dinosaurs and the age of reptiles. The fall of the giants was not the result of a single cataclysm, but a complex interplay of atmospheric, climatic, and biological changes. It was a testament to the dynamic nature of life on Earth, where extinction and innovation go hand in hand, and where the end of one era is the beginning of another. The Carboniferous era, spanning from roughly 359 to 299 million years ago, left a legacy that is both monumental and enduring, etched into the very bedrock of our planet and woven into the air we breathe today. Beneath our feet, the most tangible inheritance of this ancient world lies hidden. Immense coal deposits formed from the dense, swampy forests that once blanketed vast stretches of the supercontinents. Over millions of years, layer upon layer of plant material accumulated in stagnant wetlands, shielded from decay by waterlogged conditions and low oxygen. This organic matter was gradually buried by sediments subjected to intense heat and pressure, and transformed into coal seams that now snake through the Earth's crust. These coal beds are not merely geological curiosities. They are time capsules, preserving the carbon that ancient plants drew from the atmosphere during a period when oxygen levels soared to unprecedented heights. The Carboniferous forests acted as a planetary engine, pulling carbon dioxide from the air and locking it away underground, fundamentally altering the composition of the atmosphere and paving the way for future evolutionary leaps. When humans began to mine and burn coal, we tapped into this ancient reservoir of solar energy, unleashing the stored sunlight of the Carboniferous and returning carbon to the atmosphere after hundreds of millions of years of sequestration. This process has powered the engines of industry and modern civilization, but it has also contributed to a dramatic reshaping of our planet's climate, as the release of ancient carbon dioxide accelerates global warming and disrupts atmospheric balance. The geological legacy of the Carboniferous is visible in the vast coal basins that underlie continents, such as the Appalachian Basin in North America, the Ruhr in Europe, and the Kuznetsk Basin in Russia, each a testament to the lush, swampy forests that once dominated the landscape. These coal-rich strata are interlayered with sandstones, shales, and limestones, recording cycles of rising and falling sea levels, tectonic shifts, and the waxing and waning of ancient deltas and floodplains. The Carboniferous also left its mark in the fossil record, with exquisitely preserved remains of giant lycopsids, horsetails, and ferns, as well as the armored bark of lepidodendrons and the intricate root systems of ancient trees. The atmospheric changes of the era were equally profound. Oxygen concentrations peaked at over 30%, far higher than today, enabling the evolution of gigantic arthropods and influencing the physiology of all terrestrial life. The interplay between life and atmosphere during the Carboniferous established feedback loops that shaped the trajectory of evolution, demonstrating how biological processes can drive planetary-scale transformations. Today, the legacy of the Carboniferous is felt not only in the energy we extract from the ground, but in the lessons it offers about the fragility and interconnectedness of Earth's systems. The collapse of the great coal forests at the end of the era, triggered by climate shifts and the rise of new plant groups, led to a decline in oxygen and the extinction of many giant species, underscoring the sensitivity of ecosystems to atmospheric change. Modern studies of Carboniferous rocks and fossils continue to inform our understanding of past climates, mass extinctions, and the long-term carbon cycle, providing crucial context for the environmental challenges we face today. The story of the Carboniferous is a reminder that the boundaries between geology, biology, and atmosphere are porous and dynamic, and that the actions of life can echo through deep time, shaping the destiny of the planet. As we look back at this extraordinary chapter in Earth's history, we are confronted with both awe and responsibility, a recognition that the ancient world of coal and air still shapes our present, and that our choices will determine the legacy we leave for the future. Beneath the lush coal-forming forests and sprawling wetlands of the Carboniferous lay a world just as vibrant and transformative, the ancient seas. These vast, shallow epicontinental seas flooded the interiors of continents, creating extensive marine habitats teeming with life. The Carboniferous oceans were shaped by shifting continents, fluctuating sea levels, and a unique chemical environment, conditions that fostered extraordinary evolutionary innovation. Coral reefs flourished not as they do today, but dominated by extinct rugose and tabulate corals. These ancient reef builders formed complex mound-like structures, providing shelter for a multitude of marine species. Crinoids, sometimes called sea lilies, anchored themselves in dense meadows, their feathery arms filtering plankton from the water. Their fossilized stalks now form thick layers of limestone, testament to their abundance. The seafloor was a living tapestry. Brachiopods, with their symmetrical shells, blanketed the substrate, competing for space with bivalve mollusks and bryozoans, colonial animals that grew into delicate lace-like colonies. Trilobites, once rulers of earlier Paleozoic oceans, persisted in diminished numbers, their diversity waning as new predators rose. Among the most remarkable Carboniferous innovations were the first true sharks and their cartilaginous kin. Xenacanthus, with its eel-like body and spine-tipped head, haunted freshwater and coastal environments. In open waters, the streamlined Cladodus and the massive, fearsome Chitenacanthus prowled, while Helicoprion, famed for its spiral-toothed whirl, hinted at the evolutionary experimentation of this era. Ray-finned fishes, or actinopterygians, began to diversify, developing lighter, more flexible skeletons and advanced jaw mechanics, foreshadowing the explosive radiation of fish that would come in later ages. Lobe-finned fishes, close relatives of early tetrapods, still thrived in brackish lagoons and tidal estuaries, their robust fins a reminder of the ongoing transition from water to land. The Carboniferous seas also witnessed the rise of ammonoids, spiral-shelled cephalopods related to modern squids and octopuses. Their intricate shell patterns, known as sutures, grew increasingly complex through the period, allowing for greater shell strength and buoyancy control. Ammonoids became vital predators and prey, driving evolutionary arms races throughout the marine food web. At the microscopic level, the oceans teemed with foraminifera and radiolarians, single-celled organisms that built ornate mineral skeletons. These tiny architects contributed to the slow accumulation of marine sediments, recording subtle shifts in ocean chemistry and climate. The interplay of rising oxygen levels and nutrient-rich waters fueled periodic blooms of plankton, supporting vast populations of filter feeders and setting the stage for complex food chains. Yet the Carboniferous seas faced their own challenges: fluctuating salinity, episodic anoxia, and dramatic changes in sea level periodically reshaped marine ecosystems, driving both extinctions and bursts of diversification. In these ancient waters, the foundation was laid for future marine life. New modes of feeding, movement, and defense evolved, and the blueprints for modern oceanic ecosystems began to take shape. The legacy of the Carboniferous oceans, like that of its forests, is etched in stone and fossil, a reminder that the pulse of life has always echoed through both land and sea, shaping the destiny of the Earth. The Carboniferous era was a time of remarkable climatic transformation, driven by the shifting architecture of continents and the relentless cycling of atmospheric gases. Stretching from roughly 359 to 299 million years ago, the planet's climate oscillated between steamy greenhouse conditions and later, cooler icehouse phases, an interplay that would shape every living thing. At the dawn of the Carboniferous, Earth was a humid world. Vast equatorial rainforests sprawled across supercontinents like Laurussia and Gondwana, fueled by consistently high temperatures and elevated moisture. Warm, shallow seas fringed these lands, their evaporation feeding dense cloud cover and near-constant rainfall. Monsoon-like weather patterns dominated, driven by the immense heat differentials between land and sea, producing frequent storms and deluges that replenished the sprawling coal swamps and peat bogs. This ever-wet environment promoted the explosive growth of lycopsids, horsetails, and giant ferns. Their towering canopies created shaded understories and humid microclimates, amplifying local transpiration and feeding a perpetual cycle of rainfall. The forest's insatiable appetite for carbon dioxide, combined with relentless burial of organic matter in anoxic swamps, steadily drew down atmospheric CO2. This, in turn, set the stage for a planetary shift. As the Carboniferous progressed, the assembly of Pangaea led to a cooling trend. The southern supercontinent Gondwana drifted over the South Pole, triggering the first major ice ages of the Paleozoic. Massive glaciers advanced and retreated, sculpting the land and periodically lowering global sea levels. These glaciations sent shockwaves through the climate system, fragmenting tropical habitats and causing catastrophic flooding when the ice melted. Marine environments responded with pulses of anoxia and habitat loss, while terrestrial ecosystems experienced cycles of expansion and collapse. Seasonality intensified. In equatorial regions, the climate remained warm and humid, but higher latitudes swung between wet summers and dry, cooler winters. Periodic droughts, withered swamps, reduced oxygen levels in stagnant waters and triggered die-offs among flora and fauna adapted to constant moisture. Yet these stressors also spurred evolutionary innovation. Plants developed tougher spores, deeper roots, and new strategies for water conservation. The atmosphere itself was extraordinary. Oxygen levels soared, reaching up to 35%, nearly double today's concentration. This hyperoxygenated air fueled the gigantism of insects and arthropods, but also heightened the risk of wildfires. Lightning storms ignited vast blazes, periodically clearing swathes of forest and reshaping the mosaic of plant communities. Even the oceans were not immune. Fluctuating sea levels and freshwater influx from melting glaciers altered salinity and temperature gradients, driving migrations and extinctions in marine life. Periodic stratification of the water column led to episodes of low oxygen or dead zones, further challenging the adaptability of marine organisms. The Carboniferous climate was, in every sense, a world of extremes, a dynamic system where shifting continents, oscillating ice, and a chemically charged atmosphere sculpted the path of evolution. The legacy of these ancient weather patterns is preserved in the rocks, the coal seams, and the very bones of the creatures that once thrived in this ever-changing world. In the Carboniferous world, insects were not just background players, they were titans of their ecosystems. Elevated oxygen levels, at times reaching 35%, allowed arthropods to grow to sizes unimaginable today. These ancient insects became some of the largest terrestrial invertebrates in Earth's history, filling ecological roles that would later be occupied by birds, mammals, and reptiles. Dragonfly-like Meganeura soared through the dense, humid forests, their wingspans stretching up to 70 centimeters, nearly 2.5 feet. With compound eyes perfectly adapted for detecting movement, Meganeura hunted other insects in midair, acting as apex aerial predators. On the forest floor, Arthropleura, an immense millipede relative, crawled among the moist leaf litter, reaching lengths over 2 meters. This gentle giant fed on decaying plant material, recycling nutrients and aerating the soil as it moved. The diversity of insects in the Carboniferous was staggering. Early cockroaches scuttled through the undergrowth, thriving in the damp and shaded microhabitats beneath the towering club mosses and ferns. Giant mayflies and primitive stoneflies emerged in swarms from the still waters of ancient swamps, their brief adult lives dedicated solely to reproduction. Some, like the Paleodictyopterans, possessed piercing, sucking mouthparts, feeding on the sap of vascular plants and playing a crucial role in the spread of plant diseases and the cycling of nutrients. Insect herbivores, such as the ancient silverfish and bristletails, grazed on mosses and algae, while predatory griffinflies patrolled both air and water, regulating populations of smaller arthropods. These interactions created intricate food webs, supporting an abundance of life at every level. The presence of such large insects also influenced the evolution of early amphibians and reptiles, which developed new hunting strategies and defensive adaptations in response to their formidable invertebrate contemporaries. The success of Carboniferous insects was intimately tied to the era's unique atmospheric chemistry. Their respiratory systems, based on passive diffusion through spiracles and tracheae, flourished in oxygen-rich air, allowing them to grow larger and remain highly active. Yet this gigantism came at a cost. As the climate cooled and oxygen levels gradually fell toward the end of the period, these giants faced mounting challenges. Many would vanish, their ecological niches left open for new forms of life. Today, the fossilized wings and exoskeletons of Carboniferous insects are etched in coal seams and shale beds, silent witnesses to a time when the air itself allowed giants to rise. Their legacy endures in the diversity and adaptability of modern insects, descendants of an age when arthropods ruled the land and sky. Beneath the shadowy canopy of the Carboniferous, forests stretched unbroken for hundreds of kilometers, verdant labyrinths of life, unlike any terrestrial ecosystem before or since. These ancient woodlands were dominated not by flowering plants or conifers, but by towering leucopsids such as Lepidodendron and Sigillaria, their scaly trunks rising over 30 meters high. Branchless for most of their height, these giant club mosses unfurled crowns of spiraling leaves, forming a living roof that filtered the sunlight into dappled green. Interspersed among the leucopsids stood the robust calamites, tree-sized horsetails with jointed, bamboo-like stems. Their whorled branches formed dense thickets along riverbanks and floodplains, stabilizing soil and slowing the flow of ancient streams. Ferns, both arborescent and low-growing, flourished in the humid understory, their fronds unfurling in the perpetual twilight below the canopy. Seed ferns or pteridosperms crept like vines and sprawled across the forest floor, their broad leaves capturing every stray photon. The biodiversity of these forests was staggering. Mosses and liverworts blanketed fallen logs in the bases of trunks, creating miniature wetlands where water pooled and insects thrived. Fungi, invisible yet omnipresent, threaded through the damp soil and decaying wood, recycling nutrients and forging symbiotic partnerships with plant roots. Epiphytic plants clung to the bark of giants, exploiting every available niche. These forests were not static. Seasonal floods, storms, and the collapse of great trees created shifting mosaics of light and shadow, opening up space for new growth. In the tangled leaf litter, intricate food webs unfolded. Detritivores broke down plant matter, while predators lurked in the gloom. Ecologically, Carboniferous forests were engines of planetary transformation. Through photosynthesis, they drew down vast amounts of carbon dioxide, pumping oxygen into the atmosphere and sequestering carbon in their woody tissues. When these plants died, their remains accumulated in waterlogged swamps, forming thick peat layers that, over millions of years, would compress into the coal seams we mine today. The structure and complexity of Carboniferous forests laid the foundation for terrestrial life as we know it, shaping the evolution of everything from amphibians to insects. They were not only the lungs of their era, but architects of the deep-time world, their legacy written in stone and air. Beneath the ancient forests of the Carboniferous, a silent transformation was underway, one that would shape the future of Earth's climate and energy for hundreds of millions of years. As giant lycopsids, horsetails, and ferns lived and died, their massive trunks and foliage accumulated in vast waterlogged swamps. In these oxygen-poor environments, the usual agents of decay, bacteria and fungi, were slowed almost to a halt. Plant matter piled up faster than it could decompose, forming thick layers of peat. Over time, geological forces began their work. Layers of sediment carried by ancient rivers and floods buried the peat under increasing weight. The pressure squeezed out water and compacted the organic material, while mineral-rich groundwater slowly infused the layers. As burial continued over millions of years, the peat underwent chemical and physical changes in a process known as coalification. First, the peat transformed into lignite, a soft brownish coal. With greater pressure and heat, it metamorphosed into bituminous coal, darker and denser. In some regions, further heat and compression forged anthracite, the hardest and most carbon-rich coal of all. Throughout this transformation, volatile compounds were driven off, concentrating the carbon content and creating the dense, black rock we recognize today. Each band of coal preserved within Earth's crust is a time capsule, a record of ancient forests, their species and the climate conditions in which they grew. The layers often alternate with shale, sandstone and siltstone, marking episodes of flooding, forest regrowth and shifting landscapes. The formation of coal was not a single event, but a continuous process woven into the fabric of the Carboniferous world. These coal seams, now mined across the globe, are the fossilized legacy of a time when Earth's green engines captured the sun's energy and locked it away deep beneath the surface for eons to come.